when you have some amount of money today, it's more valuable to have it at a later time. So simply, this is the time value of money. And the interest rate is used to measure this time value of money. And we learned the fundamental theorem of engineering economy, fundamental law of engineering economy, which says that a future amount of money is equal to the present amount of money multiplied by the interest factor and the amount of the number of periods that this interest factor is applied. So for example, if we, let's say, deposit some amount of money to the bank, let's say $1,000 we deposit to the bank, and then this bank gives us interest, let's say for 7% interest rate per year, okay, annual interest rate. And after that, we will withdraw this amount, let's say after 10 years. Then what will be the amount of money that we will receive after 10 years? How do we calculate it? Basically, this is the formula to calculate this. By the way, please keep your books with you, because I want you to check, I want you to look for some interest factors with your books. During the lecture, so you will use your books to check for some numbers in the tables. So you need to learn how to read these tables. Okay, so we said that this is the fundamental law of engineering economy if we want to find the future value from a given present value. And of course, we learned the idea of economical equivalence, where two cash flows are equal to each other with respect to their economical effects and etc. And actually, using this formula, we can do the opposite. For example, if we want to know how much we need to deposit into a bank account now in order to obtain, let's say after 5 years, in order to get a total amount of $10,000. So how much we should deposit to this bank account in order to obtain this earning, $10,000 after 5 years, let's say with an interest rate of 5%. How do we find this? And we will use the same formula, but this time we will calculate P, the present value, given a future value. And this will simply be the future value multiplied by this interest factor, again to the power of n, which is the number of interest periods, but this time the interest period should be this minus to the power of negative n, because we will take this part in this calculation to this side. And with this given information, actually, we can calculate this f as 1,000, which is the present amount, plus 1 plus 0.07, so we write the interest in this way, to the power 10. 10 is the number of years, number of periods. And for this example, present value will be equal to 10,000 times 1 plus 0.05, the interest rate, to the power number of periods, which is 5, but it is minus 5. Okay, so these are the fundamental laws or formulas. But at the same time, we said that instead of using such a formula, we can represent this with a factor, interest factors, and we can say that this future amount will be equal to the present amount multiplied by a factor. And we represent this factor in this way. We want to find f, the future value, given p. Okay, so this f given p with interest rate, which is 7%, and the number of periods is 10. So this same question can be solved using this, or this p, we know that the initial amount that we are depositing to the bank is 1,000. So we multiply this 1,000 by F given P, 7% and 10. And for this example, on the other hand, we can do the same calculation. This time we multiply this future value. We know the future value and we want to find the present value. We multiply this future value by present given future. Okay, so this P given F this time. The first one was F given P. This one is P given F. It's absolutely important which way you write it. And then 5% interest rate, and the number of periods is 5. Look, we don't write -5 here. We write 5 over here. And if we want to convert this to a formula, we convert it to this one with a -5 over here. If we want to convert this to a formula, we convert it to this one with +10 over here. Okay, now it means that we have 10,000, we know the future amount, which is 10,000, P given F, 5% and 5. And in your exams or quizzes, sometimes we will ask you just write this formula without any calculation. This will be the solution. But sometimes we will ask you to write the final solution. Then when you write this factor, interest factor, how you're going to find the value, how you're going to find the solution. In order to do this, please open your books, Appendix C, on page 663. Okay, in your book, please open this page. Starting from this page until, let me see, page number, what page is this? 681. So in between these two pages, you have all these tables, pages of tables. And at each page, there is a different interest rate. So at the top, you will see on page 664, you will see that table C1. And the table C1 is for an interest rate of 1/4%, or which is 0.25%. Okay, so this table C1 on page 684 is for this interest value. In this question, look, what interest rates in this example, what interest rate we are using? In the first one, we are using an interest of 6%. So first thing, we need to find the table which is for 7%, sorry, it's 7% interest rate. And if you look, it is table number C10. Table C10. Okay, open this table, please. And when you look at this table, on the first column, you will see the number of periods, N. And as you can see here, the number of periods is 10. So you need to find the row which is for N equals to 10. And then in this row, at the top, you can see that there are different factors. So the first one is F given P. The second one is P given F. And then we have F given A. And then we have P given A. And it goes like this. Until now, we only learned these two. We haven't learned the rest yet, this part. We will learn it in today's lecture. Okay? Now look, which factor I am looking at? F given P. So this first column. Okay? So look at the first column and the 10th row. So this factor over here that we are looking at, let me clean this a little bit. So this factor that we are looking at now is, if you look at the table, it is 1.9672. Okay, so we simply multiply this value with 1000 to find the future value. That's it. Instead of using this factor, you can just use this formula and say that, okay, this is 1 plus 0.07 to the power 10 multiplied by 1000. And actually, this calculation, when you use your calculator to calculate this value, you will obtain this one. So these tables actually is for not, needing to use to calculate these values, but they are already prepared values or calculated values. So in this course, we want you to be able to use both of them. You should be able to calculate using the formula. You should be able to calculate using the factor table. In a question, we may ask you, solve this question using the factor. And in that question, if you use the formula, we will not accept it. We want you to use this factor. Or in some questions, we can ask you to use specifically the formula. And if you solve that question using the factor, again, we will not accept. You need to know both of them, okay? And it's very easy, actually. Only write the values inside the formula or just look at the table for this one. That's it. Okay, now I'm going to ask you some questions so that I want you to find these in the interest tables and write it into the chat board. Okay, so for example, P given F, 2% and 35. So what is this value? Then find this, P given F, let's say 10% and 2. What is this value? F given P, 3% and 20. What is this value? F given P, and then let me see, 25% and let me write 26. What is this value? In the interest table, when you look at this table, 35 does not exist, right? So if a value does not exist on the table, you should use the formula. Okay? If you cannot find a value in the table, then you should use the formula. Usually these tables are prepared for most common types or for most common interest rates and periods. Sometimes some periods or some interest rates does not appear in these tables. In that case, you should use the formula. Okay, and this is P given F. What formula you are going to use? This P is equal to F times, then the interest factor will be like this, 1 plus I, which is 0.02, to the power, since we are finding P given F, it should be minus 35, okay? But now I want to show you something else. I will share this Excel file with you as well, but before I need to present another screen with you, just a minute. Excel is a very powerful tool that you can use to make these calculations. And Excel includes these financial formulas in itself. So this is a table that is prepared in Excel. And as you can see, this at the top, the interest rate is 10%. And you can find, look, this is F given P. This column is F given P. The second column is P given F. And the others, we haven't learned them yet. We will learn shortly. And now in the question, I asked you to find the interest rate of 2%. So what do? Simply, if I change this 10% to 2%, everything is calculated automatically. So because why? There are formulas in all of these cells. As you can see, the first one has this formula over here. The FV, okay, B1, A3, -1. This FV is a future value. It means future value. And then inside it, it has a number of arguments. When you write those arguments, it calculates the factor automatically. Again, this P given F also has a formula. Its formula is PV, present word, okay? And it has a number of arguments. When you write those arguments, it can calculate automatically. Now, I ask you 2% interest rate with 35 periods. Now here, as you can see, you can find the 35 number of periods 35. And the thing is, this table is given, let's say, for 50 periods. But I want more. Maybe I want up to 60th period. So when you just drag it down, it will fill automatically. So for any number of periods, you can calculate the corresponding factors using this Excel. And the interest rate, for example, let me see. What interest do we have here? 6, 7. In your book, we have these interests. For example, 11% interest. Try to find that table in your book, 11% interest. It doesn't exist. But in this Excel, if you just write 11, it will calculate it automatically. Okay. So as I told you, in your book, these values are given for the most common interest rates and periods. But with the help of Excel, if you like, you can create all these tables quickly and easily. Okay, let me share the PowerPoint again. Okay, so we will do economical equivalence calculations, okay? And there are some certain type of cash flows that we face commonly in real life. And we need to, or we have some special formulas for them to find their economical equivalent cash flows in the current time or at a later time. So a cash flow can be a single cash flow. For example, during the 5-year planning horizon, there may be a single cash flow at the end of year 3. Remember, this represents year 1, this is year 2, and this is year 3, and this is the end of year 3. This is the start of year 1, which we represent as the current time. Okay, so now we can have just a single cash flow, and actually at this point we can just find the economical equivalent of this cash flow at the current time. Okay, if I ask you what is the corresponding, let's say, present value for this one, then what you are going to do is this 100 appears at the end of year 3, so it's a future value, and I am trying to find the present value, and P will be equal to 100 times, using the factor, it will be present given future, okay? And then the interest rate is not stated here. I will simply write I, okay? And then the number of periods is 3. So I'm moving this 103 periods forward. Okay, so this is one of the cash flows. And also, please be sure or learn this, get the idea of this. Now, I want to find the economical equivalent of this $100 at the end of year 5. Okay, so let me say, what will happen? This 100 at the end of year 5. What will it be equal to? Okay. Now, how do we do this? Simply, we are shifting this 100 2 periods forward, and we will use this formula. F will be equal to 100 future given present. Now, from this point of view, when we are finding this value at the end of year 5, this 3 is an older year, it's a past year. So we will call it as present. So present does not mean the current time. It means with respect to our reference points, it's a past time, it's an older time. So that's why we are saying we are finding future value given the present value. The interest rate is I. Sometimes you just write I, sometimes I%. Both of them are okay, no problem. Okay, and then, but if you are writing a number, for example 10, don't write 10, write 10%. But if you are writing I as a notation, you can write just I instead of I%. You can say this to be I. But if you are writing a number, you should write it as a percent. Okay, and then the number of periods. So don't assume that, okay, currently the time is 0 and then there are 5 years, so we are moving 5 years. No, what we are doing, we are shifting this cash flow 2 periods ahead. So simply the number of periods here is 2, not 5. Okay? And now you can ask this question. Let's assume that we have a cash flow of 100 at this time 0, and we want to find its equivalent value at time 2. Then what is this? Let's write the formula. F will be equal to 100 future given present. Okay, interest rate is I, and the number of periods is 2. Now look at this formula and look at this formula. As you can see, they are identical, exactly the same. And the thing is, if you are shifting a cash flow 2 periods forward, it's not important whether you are moving it from 0 to 2 or 1 to 3 or 2 to 4. If you are shifting it only for 2 periods forward, then the formula is the same. It's identical. It doesn't depend on at what time in the planning horizon you are shifting it. Okay? So this is one thing that most students, unfortunately, do not get the idea. But the thing is, please try to think about this. We are moving, just moving this cash flow 2 periods forward, and it doesn't matter if we are moving from time 3 to 5 or 0 to 2. Exactly the same formula. And similar to this one, if you are shifting this back from 3 to 1, the same formula is applied if you are shifting a cash flow from 5 to 3. We are shifting it 2 periods. I mean, in both cases, 2 periods. Okay? So one of the most common cash flows is just this single cash flow. But there is another cash flow which is called equal or uniform payment series. This one. And this is actually very common when you take a loan from a bank, for example. What happens? You buy an initial amount of money, you take this money from the bank, and since you are taking that money from the bank, it means that the money in your pocket increases. So this is the amount, let's say $10,000 we took from the bank. And then usually you pay this amount in equal payments back to the bank, in equal amounts. And these equal amounts are called uniform or equal payment series. Each one of them has exactly the same value. Okay? Sometimes what happens, we start with an initial payment amount, but at each year, at each period, we increase that initial amount with a constant value, for example, G. We start, for example, 50, and then in the second year, we pay 50 plus G, so it can be like this. So we start with paying in year 1, let's say 100, and then we increase our payment to 120, in year 2, and in year 3 we increase it to 140, and then we increase it to 160. And when you look at the difference, 120 minus 100 is equal to 20. 140 minus 120, it is also 20. 160 minus 140, it's also 20. So at each period, I'm increasing my payment by an amount of 20. And we will call this 20, this increase, as the G. And this series is called a linear gradient series. Okay, so you may face these kind of payment series in real life. In another one, what happens is at each period, we increase our payment not by a constant amount like $20, but we increase our payment with a constant percentage. Okay, so for example, we make our initial payment to be 100, and then we increase this payment amount by 10%, and in the next period, in period 2, we pay 121. 110, 10%. And then in the next, we increase this 110 by another 10%, so we pay 121. And we continue in this way, and this is called a geometric gradient series. Our payments increases like this. So this increase amount, which is 10%, so if you find this difference, 110 minus 100 divided by 100 is equal to 10%, 0.1 or 10%. And similarly, from this side, 121 minus 110 divided by 110, this is the base amount, and this difference is the increase, and it's again 10%. And this 10% is constant all the time. And if this is the case, it's called a gradient, geometric gradient series. And this rate of increase, in some cases, we can represent it with small g, or sometimes we can represent it with letter F. So don't be confused. This F or G, it is just the percentage of increase at each period. Okay, and this is also another common way of payment series. And finally, we may have irregular payment series or random payment series, like this one. As you can see, these amounts, it's not equal payment series, it is not linear gradient series, it is not geometric gradient series. None of the patterns applies here. It is just irregular payment series. And for all of these cases, we will learn how to find their present values, future values, and etc. And we can consider 6 scenarios depending on different types of cash flows. The first scenario can be this. Given present sum of money, so let's assume that this is our time axis, and we are given an amount of, let's say, 1,000, and we want to find its future equivalent at a later time, in year 10. Okay, so this can be one scenario. Given this present, find the equivalent future value. The second one is the opposite. This future value is given, and we want to find its corresponding present value. Okay, the future value is known, and what is the corresponding present value? Of course, we know the number of periods and also the interest rate. Okay, then this is the second scenario. The third scenario, we know uniform end of period series, and we want to find its equivalent present value. What do I mean? So we may have such, let's say, equivalent payments at each period for 10 years, okay, an equivalent payment. And we will represent these equivalent amounts with A. It is the annuity or annual payment amount. This A comes from this annuity. Okay, so we will represent the equivalent payment amount as A. So we are paying, let's say, $100, or we are receiving $100, it can be. What is its equivalent in terms of present value? By the way, look, this is just a representation. I am representing these annual amounts as upward arrows and the present value as downward arrow, or so the present value can be upward and the annual amounts can be downward. Okay, this is P and these are annual. The formulas that we use for these two cases are exactly the same. The formula does not depend on whether the arrows are upward or downward. These upward and downward arrows only shows us whether it's an earning, cash inflow, or it's a payment, cash outflow. So a scenario for this case can be like this. Initially, we borrow a loan from the bank, and then we are paying this in equivalent amounts each year to the bank back. So since we initially get this loan from the bank, this is an earning, cash inflow for us. But each year we are making these payments to the bank back. It means that it is a cash outflow. But for the second one, okay, what does it mean? We, for example, deposit some amount into a bank account. We pay this amount. It's a cash outflow. And at each year, money from the bank account. So these are cash inflows for us, earnings, and this is a cash outflow. We deposited this amount to the bank. And as I told you, for both of these cases, we use exactly the same formula. The formula does not depend on the direction of the arcs. Okay, let me quickly finish these cases and we will give a break. So the fourth scenario can be this. We have a present amount of money, we know it, let's say 1,000, and at each period we have these annual amounts and we want to find it. Okay, given this P, find this equivalent payment amount. This can be another scenario. The fifth scenario is this. We have equivalent amount of payments at each period, okay, starting from 0, and we want to find its future value. So this A is equal to 100. We are, let's say, borrowing this amount, $100 at each year, but at the end we need to pay all the money back to the bank at a single payment. What is this future value? And the sixth one is the opposite of this. We know the future value and what should be the annual amount in order to get this future value, let's say after 5 years. Okay, this is the sixth scenario.